Hello, my name is Bala Sundaram. I'm the chair of the physics department here at UMass Boston, and I'm here to tell you a little bit about a project that I worked on a few years ago. It is an interesting application of molecular dynamics simulations, and it comes in a context where these ideas actually play a very big role, and that is with these wonderfully complex things called colloidal suspensions. So the title of my talk doesn't say that quite so clearly. It's a little more convoluted. It says field-induced phases in a heterogeneous mixture of charges. And that mouthful, as I hope to tell you, is actually quite a simple idea. And all it is a bunch of charges interacting with each other and producing unusual behavior. So the starting point, the way the talk is laid out, is that there are three parts to the talk. The first part is simply a motivation, which is going to tell you a little bit about why these objects, colloids, are interesting, in particular if you put them in an external field. I'm going to deal with a specific experiment that came out in 2005, which dealt with something called anomalous orientation. I'll explain to you what that means. And that's going to provide, the findings of that experiment are going to provide the foundation for the model that I will construct. And that is what I refer to as a dynamical model. In the context of the molecular dynamics MOOC that you've gone through, dynamical model simply refers to the fact that we're not dealing with an equilibrium or a thermodynamic situation. We're actually dealing with a situation where things are actually changing with time. They haven't quite settled down. So that's the interest. And then I finally get to the results and a discussion of what they mean. So we start with the idea of colloids in external fields and charged colloids. So what does all that mean? Colloids are very interesting. They're basically objects which are suspended in another object. It could be a liquid suspended in another liquid, a gas suspended in a liquid suspended in a gas, a solid suspended in a gas, etc. And possibly the most simple example, or the most common example, is milk. It's an example of a colloid. It's a special type of colloid called an emulsified colloid, but those are just subcategories. So that's an example of a colloid. Quite often these colloids are in fact charged, meaning that they carry either a positive or negative charge. And depending on their charge, they can attract or repel each other. And they can form fairly interesting complex structures, especially when you put them in the presence of external fields. In this case, we're going to be talking about electric fields. Now, of these phenomena, and these phenomena are collectively referred to as electrokinetic. Kinetic meaning it's got to do with the motion of the charges, and electro has to do with electrostatic repulsion or electrostatic interactions. Very, very small subset of these problems are clearly understood. We have, there's been extensive studies, and quite a number of these phenomena have been well studied, but I wouldn't say fundamentally there are a large number of outstanding questions. Now, life gets a little more complicated, where instead of having just simple round colloids, they get structure. For example, they could be in the form of a rod. So like my pointer over here. Now this would be an example of a colloid where there's a shape, and it can do all sorts of things. It can spin around, and depending on which end the charge is, when you put an electric field, it can flip around and do all sorts of things. You mix and match these, and you get a very, very interesting and novel behavior. And so the motivation for this particular work that I'm going to tell you about were the results of an experiment done by Mantegazza et al., and it appeared in Nature Physics in 2005. And one of the things that they did was they took colloids shaped like this, rods, and they mixed them with little round colloids. And they put them in an electric field, and in the process they saw some very, very interesting novel effects. And so let's start by I'll showing you a little bit of the results that they found. So, and that is what is called this phenomena of anomalous orientation. So this was the experimental setup. They took dilute suspensions, which means that there are very few particles relative to the amount of the stuff they're suspended in. And these are what we're going to call primary particles. And these primary particles, as far as whenever I say primary particles, or whenever you see primary particles, you should really think of things like the pointer, like the rod. And they are in the neighborhood, they're surrounded by these smaller secondary particles, which are round. They don't have this profile. They're much smaller and they're rounder. And all these objects, all these charged objects, are placed between two plates where there's an AC electric field. And the AC electric field basically means that the polarity keeps switching, goes positive, negative, negative, positive, so on. Under these circumstances, you get this very interesting effect, which is called electrically induced optical birefringence. Now, what does that mean? The electrically induced means it's a consequence of the electric field that you put on. The optical means that you can see this phenomena by shining light on it. And the birefringence basically means that if you look at it in one direction as opposed to another direction, the refractive index is different, which means the amount that the light bends is different depending on which direction you look at it. So that's what all that means. And so what they did was they took this box with these two different types of colloids, they shone light on it, and they actually measured what they could see in one direction as opposed to shining light and looking at it from another direction. And in quantifying this, they actually calculated this thing called the Kerr coefficient. And the Kerr coefficient is nothing but, it's something which tells you how the change in the refractive index between the two orientations depends with respect to the square of the electric field. Now, this particular effect depends on the square of the electric field. Lambda is the wavelength of the light that you're using, and this B depends on the frequency of the AC field. So if you change the AC field, change the frequency of the AC field, then this quantity B changes. And B changing basically means that for the same field value and the same wavelength, the change in the refractive index could be different. So they study that, and we'll see what that allows you to do. And in the process of doing this, they use different types of these rod polymers or primary particles, and they used a range of secondary particles. And the interesting thing was, in each one of these cases, they did see this effect of anomalous orientation. So what is this mysterious anomalous orientation? So let's go to a schematic. So before we get there, a couple of things to note. If I just had the primary particles, so if I just had just the rods, and I put on a AC field, as long as the AC field was not too slow, the rods would point and switch alignment depending on as the field changed. So as the field changes polarity from positive to negative, the rods would rotate around. So that is what we call normal orientation, meaning that these particles line up with the electric field. If instead you just had the tiny round ones, since they don't have this preferred orientation, they just go all over the place. So there's what is called isotropic behavior. That means if you sat in the fluid and looked around anywhere, you would see the same amount of concentration of the small particles. When you put both of them together, the rods as well as the round particles, that's when you get anomalous orientation. So schematically, let's just recap. If we just had the primary particles, they line up with the field. So here you can see that these blue rods are lining up with the field. If I had the round particles, the secondary particles, which are described as the pink dots, if I just had those, they would just be in some pattern. No pattern, I'm sorry, just distributed almost homogeneously. If you put them both together, there's some frequencies, some range of frequencies and some range of field strengths for which they line up just like they did before. So here you can see, with or without the secondary particles, they have the same behavior. However, the interesting part of the anomalous orientation is when you see this, which is the field is pointing this way. This is where it wants to line up. And the rods actually line up in a direction that's perpendicular. And so the orientation is anomalous, meaning it's actually doing something which it's not supposed to do. Why isn't it supposed to do this? Because energetically, this is the much more comfortable state to be in. This costs more energetically, and so this is not something you'd normally expect them to do. So here's the schematic, and this is the picture that I'd like you to keep in your mind as we continue talking about this in terms of the quantitative measure, which is the Kerr coefficient. So in terms of the Kerr coefficient, this is what you get. When you've got just the primary particle, just the rod, and you notice here what we're changing up here is the frequency of the AC field. So as you change the frequency of the AC field, as the AC field the frequency goes up, which means it changes direction faster, you see that the rods go from a situation where they go from a positive value, and positive value basically means that they align the way they're supposed to be. And when it gets to high frequency, you get an effect where if the field is switching around too much, these things, it's too fast for these things to respond, and they just basically stay where they are. So that's what this says. If you just had the small particles, the round ones, then you see no special effects. Let me go back to where I was. So here you see no special effect, meaning that there's no preferred orientation at all. Now you get this anomalous case. In the anomalous case, you notice that this B value is negative. And it's negative for a range of frequencies. And so you can see that there's negative for a range of low frequencies. So for the low frequencies, you see from here to here, the value is negative, which means that you have an orientation like this, the anomalous. As you continue increasing the frequency, it becomes positive, in which case you go back to normal orientation. So it's normal orientation over here, and anomalous orientation over here. And then when the frequency gets too high, it doesn't respond again. So the lesson to be learned from this quantitative measure is when this value B is negative, then you think of it pointing in the counterintuitive direction, whereas when it's positive, then it's pointing in the usual intuitive direction. Now, using this measure, now that we understand how to interpret it, they did several things. So let's take a look at A first. So this is one where they kept the round colloids, the small ones, the same, but they used a variety, 4 different types of rod. And so you can see for each one, it doesn't matter which one it is. Notice the first one, the green one, is E. coli. So it's the E. coli bacteria. And so the bacterium is a polymer. So it has charges that run up and down, behaves exactly like a rod. And there you can see there's a small range of frequencies for which it's negative, meaning it points anomalously, counterintuitively. And then it increases. As you increase, it goes into the normal orientation. But you notice that for every single one of these cases, there is a small range of frequencies for which it behaves anomalously. So that's the inference drawn from the first one, that the anomalous effect is seen for different primary particles and using the same secondary particle. Then let's go to the next one. Here what they've done is they've picked one of these, but they've changed the round, small secondary particles. And once again, you notice that it doesn't matter which SP you use, that for all of them, you see a set of values of frequencies for which B is negative, meaning that it's pointing in a direction that you don't expect it to. And then, of course, it settles into the normal orientation at higher frequencies. So in each of these cases, the trend is exactly the same. Now, you might say, well, maybe it's all got to do with the rod polymers and what happens to the rod polymers. Well, one of the things that they did to check that is they changed the concentration of the rods. So if this number is small, that means there are very, very few of these rod polymers. And if the number gets bigger, as the number gets bigger, you add more and more of the rod polymers. And one of these things you notice is if you scale the curves, all of these curves essentially lie one on top of the other. So that means it actually has very little to do with the rod polymers. It mostly has to do with the little guys. In fact, the behavior that the inference that you draw from this is that the anomalous behavior is actually each of these rods surrounded by a bunch of acolytes, which are the little small polymers. So this is important for us because what this tells us is we could actually build a model with a single rod surrounded by a bunch of particles, and that might already tell us part of the story. And that's exactly what we're going to do. And then finally, the size of the effect, which is given by how negative this becomes, depends on the charge of the primary particle. The primary polymer, if it's more charged it is, the bigger the effect. And you can see that it's bigger both in the negative direction as well as the positive direction. That means both the anomalous orientation as well as the normal orientation are affected by the charge. So now we're at the stage where we've talked about the motivation for the model that I'm going to tell you about. And based on their findings and what else is known about these types of systems, we can now put together the underlying assumptions behind the model that we're going to construct. So based on what we have a number of underlying assumptions. And the first thing I want to do is the following. If we go back to this picture, you notice that each of these things, I can draw a little box around it. And if I draw a box around this one or this one, the neighborhood looks exactly the same. So that is what I'm going to call a cell. So the underlying assumption in our model is the fact that the fluid is made up of cells. And each cell has a single charged rod, which is our primary polymer. And it's surrounded by several small charges, in our case they're point charges, which have the same sign as the charged rod, but they're the secondary polymers. So our rod just consists of a simple rod with two charges at the ends, and then our little charges are point charges that are running around. And all of these interact with an AC electric field. Now we impose periodic boundary conditions, and what that means, going back to the picture that we had here, is that here's a cell and here's another cell, which means that if a particle goes out of this cell, it goes into the cell of the neighbor. So that's a bit like going out at one end and coming in the other end. And similarly, if it goes out the top, it goes into the neighborhood of another rod, which means that's a bit like, again, going out the top and coming in through the bottom. And that's what we mean by periodic boundary conditions. So we've got periodic boundary conditions, and that, as I said, just said that the secondary particles can move from one cell to the neighboring cell. Neighboring cell being up, down, right, or left. What's our motivation for doing this? There is this effect in physics called frustration. And frustration comes from the fact, and all of us have experienced it at different points of our lives, is the fact when lots of people want you to do lots of different things. What do? Well, if there are a few things, then you manage to multitask and take care of it. Well, if there are too many things, then you get frustrated because you can't complete many or most of the things. That's exactly what happens to these particles. If there are too many counterbalancing or countermanding influences, it can't really satisfy all of them, or when I say it could either be the small particles or the big ones. If they can't fulfill all of them, then they actually do something weird, unusual. And that's what we'll see happens in this case. So that's our motivation to see if, in fact, this is a possible explanation for this anomalous orientation. There's a caveat here. Charged colloids in real suspensions are very, very complicated. Things move around with time. There are hydrodynamic effects that need to be taken into account. And to get taken together, they call electroosmotic effects. We're ignoring all of them. We're simply looking at it from an electrostatic perspective and asking ourselves the following question, which is that can a simple model which takes into account what are called collective plasma effects, meaning collective effects of lots of charges, is that sufficient to capture the essence of this anomalous orientation? So that's our motivation. Okay. So now what are the variables? Well, we have a rod. And whenever you have a rod, it's a composite object, meaning it's made up of lots of particles. So you need to think about the center of mass. So we have to look at the position and the momentum. And by the way, the fact that they're in bold means they're vectors. So in our case, we're going to deal with a two-dimensional model. It could easily be three-dimensional. So we're going to do with two-dimensional. So it's a two-dimensional vector, position and momentum. And that denotes the center of mass of the bar. Each of the secondary particles, which each of the small point particles, has their own position and momentum. And there are n of them. We'll say what n is in a little bit. Then, of course, this rod needn't point straight up. It can tilt, which means we need an angle to describe the angle between the bar and the x-axis. And so the way we do that is through this angle, which we call theta. And also, based on that angle, we can specify the two ends of the rod, which are R1 and R2. And R1 and R2 are related to the center of mass position through the simple relationship. So this corresponds to a rod which has a length of 2L. You've got a mass and a charge on each of the small particles, which is m and q. The bar itself has two masses, which are m over 2, and they have two charges, one at each end. You've got the amplitude of the field, you've got the frequency of the forcing field. And just to make life easy, we make everything dimensionless, meaning we don't have to worry about whether it's in centimeters or meters or whatever, by measuring space in terms of the length, half the length of the bar, masses in terms of the mass of the small object, charges in terms of the charge on the small object, and time in terms of the inverse of the frequency that we impose. So what this allows us to do is it allows us to write the Hamiltonian, or the energy of the whole system, like this. And it has contributions that we can now walk through. So this is the kinetic energy of the center of mass of the bar. This is the rotational kinetic energy of the bar. This is the kinetic energy of each of the individual small particles. This is the electrostatic interaction between two small particles. This is the electrostatic interaction between one of the small particles and one of the charges on the rod. It depends on which end it is. So depending on which end, it either uses Q1 or Q2. And then finally, this is the interaction of the small particles and the rod with the external electric field. And you notice there's a J in front of the external electric field, and the J just means that it's pointing in the Y direction. So as far as our orientation is concerned, when we say vertical, that's the same direction as the electric field. So this is the Hamiltonian. From the Hamiltonian, we can derive Newton's equations. And you've heard throughout the course, ultimately molecular dynamics is about the solution of a set of Newton's equations. And here they are. And so this one is the equation for the second order differential equation for the rod, center of mass. This is for each of the particles. And you can see that xi means that there are n of these equations. And then this is the equation for the rotational part. And over here, these quantities q tilde and n, etc., are all in terms of the scale that we talked about, which is the mass of the little particles and the charge on the little particles. There are two parameters that we're left with. And the two parameters are this, and which is the coupling, which tells you something about the coupling between the two small particles, and this, which is some dimensionless measure of the field strength. So it doesn't just say the absolute field strength outside is so many volts per centimeter. It puts it into perspective of some internal. Now, this life becomes much easier if we do what we do in physics quite often, which is to set the mass and the charge and the length all equal to 1. And if we do that, then it turns out that this just goes as 1 over the frequency of the electric field square, and the field goes as the field divided by the frequency square. So this is like a dimensionless length, if you like. In the simulations that I'm going to show you in all the results, the number of small particles I've taken is 50, unless I specify otherwise. Also, if you remember, when we go back to the Hamiltonian, you have this Coulombic interaction, which basically means that when those two distances get very small, it gets very large. And very large numbers make the differential equations much harder to solve. And so one of the things we do is we use a trick. It's called softening the Coulomb singularity, which basically means that when you get too close, you actually flatten out the potential, which means it can grow stronger, but it can't grow stronger beyond a certain point. This actually turns out to be not very significant, and there are real-world reasons for actually softening the singularity. We can make things more complicated if we want. We could add friction. We could make charges at the ends of the rod change with time. And we could introduce screening effects, meaning that if there's a charge sitting between me and you, then I'm going to feel less of an influence. So that's called screening, and we can put those in. But at the end of the day, ultimately, there are only two free parameters that I can change. One is the frequency of the external field. The other one's the strength of the external field. So what is plotted here, and actually there's an enormous amount of information, because as you can see, what is plotted is log to the base E of the electric field. So this is about 3 or 4 orders of magnitude in terms of the variation in the electric field, and it's again, about 2 orders of magnitude in this direction in terms of the variation of the frequency. And what is plotted here is the angle of the orientation of the rod with respect to pi over 2, which means 1 corresponds to an angle of pi over 2. Don't forget, the angle is measured from the horizontal. Pi over 2 basically means that it's pointing up in the y direction, which means it's in the same direction as the electric field. So that means whenever you see red, it means it's the normal orientation. And wherever you see blue, the angle is 0, which means it's the odd orientation. So that means if I draw a line going across here, what I'm doing is I'm fixing the strength of the electric field, but I'm varying the frequency. And one of the things you see is that for a range of frequency, you see horizontal, which is the anomalous orientation. And for another range of frequencies, you see vertical, which is the normal orientation. So you're actually moving from anomalous orientation or the funny orientation to the normal orientation through something which we will, in the paper we argue, resembles a phase transition. Over here, the green corresponds to a random orientation. So at very low frequencies, it's what happens is an odd particle comes close by and gives it a little kick, and the rod moves around and settles in at some angle. And if you do some, as a function of time, that angle varies randomly. And when you average it, you get an average value of pi over 4, which is what you're seeing. So you get this very funny effect. And so if I plot this, which is what is drawn here, this line, as you can see, this is in units of pi over 2. This is pi over 4. So it's random here. It becomes horizontal, and then it becomes vertical, and then it goes to essentially the initial, this dotted line tells you what the initial orientation of the rod is. So in the high frequency, it doesn't move. So once you get to the high frequency, the rod is, the field is changing too fast for the rod to respond, and it just stays in the orientation that you put it in initially. So this is a curve that we can completely understand. Now the funny thing is, we can do something else. Here what is plotted is we started off with some value, and this is what the angle of the orientation of the rod does with time. And this time is measured in cycles of the electric field. So this is 20 cycles of the electric field. Similarly, this is another one which starts off at a different orientation, but you notice this one goes to pi over 2, this one goes to 0. So pi over 2, don't forget, is the normal orientation. So when we look, so here's the rod. The rod is somewhere in the middle here, and this is our cell. The rod is in the middle. It's pointing in the normal orientation. But you notice that the little particles are distributed all around the outside with a large concentration at the ends, at the corners. So this is very different from this situation where you notice that the little particles, this is plotting the concentration of the little particles, and the bulk of the concentration is above and below the rod. So you notice that depending on whether it's the normal orientation or the anomalous orientation, the distribution of the small particles is fundamentally different in the two cases. In the normal orientation, they're in the corners, whereas in the anomalous orientation, they stack up above and below. And the funny thing is that if you go back to that picture that I took from the experimental paper, this is the anomalous orientation. And notice that the way they asked the artist to draw this picture is to stack these particles above and below. And here they're much more evenly distributed around. And so they did have an idea for what might be the cause of this effect. And they were guessing that this would be one of the implications. And we found this in our molecular dynamics simulation. So what are our conclusions? So the first thing is that the distribution of those particles is strikingly different. The normal, they lie at the corners and the periphery. The anomalous, meaning the odd orientation, they occupy a much larger fraction of each cell, and that they're clustered closer to the primary particle. And the random orientation is most likely dominated by single events, meaning some one particle getting a little too close for comfort, which nudges things. The other thing which is sort of interesting in our model, which the experiment doesn't have, is the fact that we have this cell. As you can see here, the cell is 3 units in this direction and 5 units in this direction. So the ratio of the x to y is 3:5. Now, of course, the normal orientation is this way. meaning the rod is supposed to be longer, the rod itself is longer in this direction than in that direction. So how does that affect things? So in order to, we ask this question, and in order to check it out, we frame the question in the following way. How does the phase diagram get affected by the aspect ratio? The aspect ratio is just the ratio of the length to the height of the box. And here there are two diagrams. The top one is the one you saw a few minutes ago. It has the random, it has the horizontal, it has the vertical. And this is, the ratio is 3:5, just like I showed you. So the x is 3, the y is 5. This is a square box, 4, 4. And notice what happens. The anomalous part is gone. So now you only have the random and the normal orientation. You don't have the anomalous orientation anymore. In fact, take a look at a few more results. This is the 3:5. This is the 4:4 with 50 particles. This is the 5:3. So here what I've done is, you would think there's no difference between 3,5 and 5,3. There is. And the reason is because the electric field is pointing in the y direction. And so now the short side is along the y direction rather than along the x direction. I mean, the short side is along the y direction rather than the x direction that we had before. That's right, got it right. But that makes a difference. If you switch to a 3,7, which makes it even longer along the y direction, then you get the anomalous phase back again. If you switch to the 3,5 but reduce the number of particles, 50 particles, 30 particles, 10 particles, 2 particles. So there are very few particles, it vanishes again. So you need some minimum concentration of the small particles in order to see this anomalous effect. But this clearly points to the fact that the small particles are responsible for this effect. So it again verifies what the experiment was speculating. And then finally, this is 50 particles with it doesn't necessarily have to be a ratio. This particular area is also interesting, and I'm not going to get into that here today. So what are our conclusions? Well, the conclusions are, the first and foremost, that the anomalous effect is clearly driven by the small particles, the secondary particles. There's a minimum concentration necessary for this to occur, and they have to be able to aggregate above and below the rod in order to allow for the anomalous orientation. And the reasoning is really, this is why the 3,5 works rather than the 5,3. Because in the 5,3 there isn't enough headroom for these small particles to accumulate above and below the rod. In fact, there isn't enough headroom for the rod to stand up straight. So the competing influences of the electrostatic potentials that act between the small particles and the rod and amongst themselves with the electric field, and the frustration that comes about from that, is what leads to this effect, because it's trying to satisfy all these electrostatic impulses. There are all forces acting on it, each one's trying to push it in a different direction, and the net result is it does something which is a compromise, and the compromise need not be the most energetically favorable one. And this is the idea that we're now trying to explore, that there is the picture that one sees when you change the frequency and the field strength of the electric field looks very close to a phase diagram that shows up in all sorts of physics and condensed matter physics, and this is something we'd like to explore some more. And finally, from the standpoint of molecular dynamics, you could do a much more complicated or complex molecular dynamic model where we could include the hydrodynamic effects as well, and not just the electrostatics. In which case, yes, it would be a lot more complicated. Yes, there'd be more equations to solve, but it'd be much closer to the effects that are seen in real colloidal suspensions. Much of what I've said here and more is contained in this reference, which is a paper that I wrote with a colleague of mine, Carlo Lancelotti, as published in the journal Chaos in 2008. I hope this gives you a sense for where molecular dynamics and the ideas that you've encountered in this MOOC may prove useful. Thank you.